Hey guys, today we will be talking about vectors as derivatives. Now in this entire video, we will assume that you know tensor algebra, which means that you know how tensors act on other tensors. You know how tensors transform under coordinate transformations, and you know multivariable calculus. Now in this video, we will be talking about how vectors, such as the EX basis vector and the EY basis vector, can be rethought of as derivatives, in this case partial derivatives. And this idea may seem wacky or weird at first, but it actually becomes really convenient and in a short time becomes pretty normal if you practice it enough. So here is a proof for basis vectors, specifically being partial derivatives. Now in this proof you have to set up a few things first. Here R is what's called a position vector. R, x, y just means a vector R going to the point x, y. That's all it means. R, x, y is just a position vector. It's a vector going from the origin to the point x, y, some arbitrary point x, y. And then here we have Rx plus hy. That's just going to be Rxy, but we're adding h to the x coordinate, which is shifting this basis vector by some amount. That's what it means. And then we have R of x plus hy minus R of xy, which simply is just the separation vector between those two vectors. Now, when we take the limit of this whole thing, you take the limit. And just saying it, yeah. H is just the distance that it's being shifted. So when we take the limits of this whole thing, we get the partial derivative of R with respect to x, which would equal the EX basis vector. The EX basis vector is just a unit vector in the x direction of a Cartesian space, of Cartesian coordinates, x, y. So that's what it is, and this actually makes sense, because this is, of course, set up in the famous derivative way. We have f of x plus h, f of x plus hy minus f of x y over h. That's obviously the definition of a partial derivative. Okay, so it makes sense mathematically, but how does this make sense intuitively? Well, what we're really doing is we're just dividing by h, and this over here is pretty much the length of the vector. When I subtract this by this, I'm gonna get the length. You're gonna get kind of the length of. You can think of this vector as just the length, okay? And you're dividing the length of the vector by h, which would keep the vector normalized. So let's say I had a vector, okay, and this vector had a length of 3. If I divide the vector by its length of 3, we will get a unit vector in that direction. So it makes sense how it's going to be a unit vector, because we can kind of think of this as a length. It's not really the length, it's just the separation vector. But when we divide it by h, because h can be thought of as the distance actually, when we divide it by h, we're going to get a unit vector. And if we're going to get a unit vector, and this vector is already completely in the x direction, that's just the position basis vector. So it really makes sense. So if h is the distance between these 2 points, and we're dividing by h, well then it's gonna be a unit vector. And when we divide vectors, when we multiply vectors by a fraction, it's gonna stay in the same direction, but it's just gonna get scaled a bit. Except if the fraction is negative. So that makes completely intuitive sense, and you can use the same logic for the EY basis vector, as you can see over here. And this applies for all basis vectors. So all basis vectors can be reinterpreted as derivatives. So when you see something like partial r over partial x, I don't want you thinking of some limits of a function in your head. Don't do that. Think of these itself as the derivative. It's like saying that, it's kind of like saying that 5 is, it's like saying that 0 is the derivative of 5. It's like saying that with respect to x. It's kind of like saying that. Is 0 an actual derivative of 5? Well, not really, but it's equal to the derivative of 5. A basis vector is equal to the partial derivative of x, well, the partial derivative of a position vector r with respect to x. It's equal to that. But you could also really think of it as a partial derivative of r with respect to x is that basis vector. That's how I like to think of it, and it's not wrong. So when you see this, think of the basis vector. Don't think of the computation. Think of the actual vector itself. So this may seem pointless to you. Why should we throw away our old intuition of vectors? Why make basis vectors partial derivatives? Well, this actually helps a lot, because we know from multivariable calculus that the derivative of a function with respect to some parameter lambda is going to be dx over, it's going to be dx over d lambda partial f over partial x plus dy over d lambda partial f over partial y. That is called the multivariable chain rule. And since basis vectors are partial derivatives, you can do something similar to it, right? You can say that a tangent vector in this case, dr over d lambda, equals dx over d lambda times partial r over partial x plus dy over d lambda partial r over partial y. So since we can write basis vectors as partial derivatives, that means that we can write tangent vectors or tangent vector fields as just normal derivatives by using the multivariable chain rule. And this comes in handy when trying to measure a tangent vectors along some arbitrary path in a field. So let's start using this new way of thinking of derivatives, and this new way of thinking of vectors to our own use. Let's say that I have a coordinate system, the xy Cartesian space, where x equals lambda and y equals lambda squared. So y pretty much just equals x squared, and lambda is our parameter, of course. So let's first draw this graph. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, I'm going to just do something a bit different. Let's actually change. Actually, no, we're going to keep it like that. So, this is our parameter. And we can go ahead and graph this already. For lambda equals 1, our points are going to be 1, 1. So we can graph that. And then we have 0, 0, of course. For lambda equals 2, we're going to have the points 2, 4. 2, 4. For lambda equals 3, we're going to have the points 3, 9. Here's 3. And then 9 is like right over here. And then we can't graph the rest because the graph is going to go off. But the path is going to look something like this over here. It's going to be a curve. So here is our path. We can call it, yeah, that's just our path. So we can call this path R of lambda. That's just what we're gonna call the path R of lambda. So let's say that we want to find our the tangent vectors along this path. Well, we just use multivariable chain rule. dr over d lambda is going to equal dx over d lambda times partial r over partial x plus dy over d lambda partial r over partial y. So dr over d lambda equals, well, what's dx over d lambda? What is that equal to? Well, if x equals lambda, then d lambda over lambda is just going to be 1. D lambda over d lambda just equals 1, obviously. So it's just going to be 1 times partial r over partial x plus dy over d lambda. Well, if y equals lambda squared, then dy over d lambda is going to be 2 lambda plus 2 lambda. Yes. Partial r over partial y. We can simplify things a tad bit. dr over d lambda equals partial r over x plus 2 lambda partial r over partial y. Now, it's good to note that this is our tangent vectors. Here is our x unit vector. Here's our y unit vector. And as we can see, we have a tangent vector field where at different points of lambda, we are going to get different vectors, different tangent vectors for different points for different lambda values. So here we have a tangent vector field. Our tangent vector isn't constant throughout this path. So for lambda equals 1, you have the points 1, 1, 1. Our tangent vector is going to be d partial r over partial x plus 2 partial r over partial y. So it's going to be like this. Here's 1 partial r over partial x, and then 2 partial r over partial y. Right here. Let me just draw that vector right there. That's dr over d lambda for that point. What about for the origin? For the origin, that's just going to be partial r over partial x. The tangent vector is going to look something like this. How about for lambda equals 2? limit equals 2. It's just going to be 4 partial r over partial y plus partial r over partial x. So lambda equals 2. Where is that? Lambda equals 2, 4. As it can be 4 partial r. One, 2, 3, 4. And that makes sense because at 4, that's where it meets a curve. 1, 2, 3, 4 meets the curve right there. And we get this tangent vector. Oops, that's kind of bad. Gets this tangent vector right here. dr over d lambda. So if we just remove all that nonsense, all this junk over here, let's just move it down. We can just move these away. And we can see that this is what our tangent vectors would look like along this path. And it makes sense because when we start off, we can think of tangent vectors as velocity, right? And we can think of the change in tangent vectors as acceleration. So at the start, our velocity is pretty small, but it gains velocity. But this ball or whatever object is having this path, it's gaining velocity as time, which would be the x-axis, goes on. It's gaining velocity. It's gaining momentum, which is why this vector is going to grow. Not to change direction, but it's gonna grow. And we see that it's growing because of that 2 lambda term. That 2 lambda is making the y basis vector actually change from point to point. So that's just one example of using this new technique that we've learned. And we will be practicing it more in the future. Thanks for watching. Have a great day. Stay safe. See you guys in the next video. Bye.